Hey everyone, welcome back. Now that we've got a basic understanding of what quantum computing is and why it's so special, let's dive a bit deeper. In this video, we'll explore how quantum computers actually work, from how qubits are built to how they're controlled, and finally, how they perform calculations. Before we jump into new stuff, let's do a quick recap. Classical computers, like your phone or laptop, use bits, which can be either a 0 or a 1. Quantum computers use qubits, which can be both 0 and 1 at the same time. And remember, those three important ideas, superposition, entanglement, and interference, they're what make quantum computers so powerful and weird at the same time. So what exactly is a qubit? Well, scientists have found a few ways to make them. Some are made using superconducting circuits that need to be super cold, close to absolute zero. Others use single atoms or ions trapped with lasers, or even particles of light called photons. Each method had its own advantages, but also its own challenges. The goal is to find one that's stable, scalable, and accurate. One of the most important and popular types right now is the superconducting qubit. These are tiny loops of superconducting wire with something called Josephson junctions. You can think of them like artificial atoms that can exist in multiple energy states. To keep them working, they need to be incredibly cold, just a few thousands of degrees above absolute zero. Scientists then use microwave pulses to control and read them. IBM, Google, and Rigetti use this design in their quantum computers. Another amazing type is the trapped ion qubit. Here, individual ions, basically charged atoms, are suspended in electric fields and manipulated using lasers. Each laser pulse changes the state of the ion, which acts as a qubit. These are extremely precise and stable, but the downside is that it's hard to scale them up to large numbers. Imagine trying to control hundreds of individual atoms at once. Once we have qubits, we need a way to control them, and that's where quantum gates come in. Quantum gates are like the logic gates in classical computers. But instead of flipping bits from 0 to 1, they rotate qubits on something called the Bloch sphere, a 3D way of showing a qubit state. By applying different gates in sequence, scientists can build quantum circuits that perform algorithms. Quantum algorithms are basically sequences of gates. For example, a Hadamard gate puts a qubit into superposition, and CNOT gate links two qubits together through entanglement. At the end of a quantum computation, the qubits are measured, and that measurement collapses their states into classical bits, which is zeros or ones, that we can actually read. So the quantum part happens before the measurement. That's where all the magic is. In classical computing, everything is deterministic, meaning we know exactly what happens at each step. On the other hand, quantum computing is probabilistic. It explores many paths at once, and the final measurement gives us most likely correct answers. It's like trying every path in a maze at the same time instead of walking one by one. Which one's going to be faster? Of course, quantum computing. One of the hardest parts of quantum computing is keeping qubits stable. They're super sensitive to their surroundings. Even a small vibration or a bit of heat can mess them up. This is called decoherence. To fix this, scientists use quantum error correction, which means combining many physical qubits to create one logical qubit that's much more stable. But this takes a lot of resources, so scaling up is still a major challenge. When you look inside a quantum computer, it doesn't look like any laptop or desktop. Instead, you'll see a massive cooling system called a dilution refrigerator. So it keeps these qubits cold enough to function. There are layers of control, electronics, signal wiring, and electromagnetic shielding to block interference. The actual quantum chip, it's a tiny square at the very bottom. So the most important part is the smallest part at the very bottom. Right now, companies like IBM, Google, Rigetti, and IonQ and D-Wave are leading the field. What's really cool is that you can actually try quantum computers yourself. Platforms like IBM Quantum Experience and Amazon Bracket let anyone run small quantum programs through the cloud. These systems are still experimental, but they're improving every year. So what's next? The big goals are to scale up the number of qubits, reduce noise, and make qubits last longer before decohering. Researchers are also working on hybrid systems where classical and quantum computers work together. Classical processors handle everyday stuff, while quantum ones take on the hardest problems. The combination could change everything. Imagine the potential of quantum computing. Let's wrap things up. Today, we learned how qubits are made, how they're controlled using gates, and how quantum computers perform real calculations. We also looked at their challenges like noise and stability, and how scientists are working to fix them. The field is growing fast, and every year we're getting closer to practical, powerful quantum computers. In our next video, we'll take the next step, how quantum computers actually solve problems. We'll explore algorithms like Grover's and Shor's that use the power of quantum mechanics to do things classical computers could never do. Stay tuned, it's going to be a fun one. Thank you. See you next time.